In this video, we're going to talk a little bit more about refrigerants. For those who have a Modern Refrigeration Textbook 20th edition, this goes along with Chapter 9. So we want to recognize the effects of halogenated refrigerants on the ozone layer. We want to be able to summarize the EPA regulations governing refrigerants, and we want to be able to differentiate between CFC, HCFC, HFC, and other blended refrigerants. You want to be able to identify refrigerants according to their series number and cylinder color codes. We want to be able to interpret pressure to temperature curves, pressure-enthalpy tables, and pressure-enthalpy diagrams. We want to be able to summarize the properties and common applications of different refrigerants, and we want to be able to identify which types of refrigerants are compatible with what lubricants. So the ozone layer filters ultraviolet radiation. It protects humans, plants, and animals, and it maintains stable temperatures. Ozone depletion may have harmful effects. It causes increase in skin cancer and eye damage, and it also causes climate change. So the Montreal Protocol banned the production of CFCs, chlorofluorocarbons, and resulted in a development of new refrigerants. Okay, so the normal ozone layer is the blue in the picture, okay, on the left-hand side. It blocks a lot of UV radiation. The depleted ozone layer is much thinner and has holes. It allows increased UV radiation to reach the Earth. The Clean Air Act, CAA, is a federal law. It provides guidelines, restrictions, and penalties for releasing refrigerants into the atmosphere. You can have fines up to $37,500 per day for failure to comply. The results of the Clean Air Act was training and certification required to handle refrigerants, prevention of significant and purposeful releases of refrigerants into the atmosphere, and exceptions to allow HVAC technicians to do their jobs. There's ways to measure the impacts. The ozone depletion potential compares refrigerants to R11. Numeric values are assigned to each refrigerant on a scale of 0 to 1. Value of R11 is 1. The global warming potential, GWP, is a ratio of a substance warming effect to that of carbon dioxide. The higher GWP, the higher risk of environmental damage. So this chart shows ODP and GDP of refrigerants. Okay, if we look at R12, which is a CFC that's no longer in production, we have an ozone depletion potential of 1. That's because of the chlorine. The GWP potential, global warming potential, was 10,900. Now, if we take a look at 134A, which is one of the newer refrigerants, it's an HFC. Doesn't have chlorine in it. 0 ODP, that's ozone depletion potential, because chlorine was the primary problem. And it has an ozone depletion or global warming potential of 1430. R410A is the other new refrigerant that you're going to use very frequently in residential and commercial air conditioning. It has it's an HFC, hydrofluorocarbon, does not have any chlorine in it, has an ODP of 0, but a GWP of 2088. Now there's other refrigerants, but they all go along with the same potential. They've all been rated for environmental properties. The first halogen-based refrigerants contain chlorine, fluorine, and carbon, CFCs. Chlorine atoms break down the ozone layer. It's a major cause of ozone depletion. They're no longer made, but they're still found in some pre-1995 equipment. The next line of refrigerants were the HCFCs, hydrogen, chlorine, fluorine, and carbon. It's partially halogenated. They have less of an impact on the ozone layer than fully halogenated HCFCs, but they have a high GWP. EPA is requiring phase out of these by 2030. R22 and R123. R22 The primary use of this was in comfort cooling, air conditioning. The newer refrigerants are composed of hydrogen, fluorine, and carbon. It's partially halogenated, has no chlorine atoms. ODP is 0, but it still has a high GWP. Okay, and that's because of the carbon. It's being replaced by lower GWP alternatives, but replacements are actually a lot of times more expensive and they're more difficult to handle. 134A, 410A, and 404A fall into this category. So when we look at the refrigerant classifications, it's all based on the molecular structure. Do I expect you to know these? Do we have to memorize the actual structures? No. But we do need to know CFC, HCFC, and HFC refrigerants. Okay, CFC is phased out. They have to be replaced. You can't buy them any longer. HCFCs are the R22s of the world. They're on their way out. HFCs are 134A and 410A. Okay, those are the current line of refrigerants. Refrigerant blends are a mixture of 2 or more refrigerants. You have 3 types of blends. You have azeotropes, zeotropes, and near azeotropes. Blends are still classified by their component refrigerants, CFCs, HCFCs, or HFCs. You cannot attempt to make a zeotropic or an azeotropic blend. This has to be done in factories and under pressures and temperatures specific to the blends. Okay, you cannot mix refrigerants in the field. They respond to changes of pressure and temperature like a refrigerant. They maintain constant properties. They most contain a phased out refrigerant. They're often called azeotropes. For some of them, each component responds individually. They have a range of boiling and condensing points. They fractionate. There's fractionation of the individual refrigerants within the systems. There's temperature glides, and they can phase and change temperature simultaneously. Newer refrigerants are out there. HFOs, hydrofluoroolefins, 0 ODP and low GWP. Okay, HFO 1234YF is in some automatic AC systems. HFO 1234ZE is in some residential and light commercial AC heat pumps and commercial refrigeration. The other one is HC, hydrocarbons, 0 ODP and low GWP values, but they are highly flammable. They're used in newer standalone and refrigerators and freezers. Now, some of these, for people who've dealt with gas heating and some of the other heating side of things, these will sound familiar. The R600A is isobutane, R290 is propane, and R441A is an HC blend of the two. Okay, if you come across equipment that uses HC, okay, like R600, R290, and R441A, you cannot use your existing recovery equipment, and you cannot use your vacuum pumps on these equipment. You have to have specialized equipment to service these. So to identify refrigerant, the first digit indicates the refrigerant series. Okay, the significance of the remaining digits depends on refrigerants. Okay, so first digit is the series. Series 0 is methane based. Series 1 is ethane based. Series 2 is propane based. Series 3 is cyclic organic. Series 4 is refrigerant blends, zeotropes. They separate. Series 5 is refrigerant blends, azeotropes. They maintain as a single one. There's there's the 600 series, miscellaneous organic. There's 700 series, inorganic. And there's the 1000 series, unsaturated organic. So the first digit, for example, 134A, says it's ethane based. R410A, it's a Zeotropic blend. It will have a temperature curve. R502, it's a blend. It's an azeotrope. It behaves as a single refrigerant. R22, okay, 22. So the 0, 1, 2, 300 series, 4, 5, 600 series. Third number from the right indicates the series. Okay. The next two numbers are assigned sequentially or denotate the number of carbon and hydrogen atoms. Okay. So we have the refrigerant that says R, it's a refrigerant. We have 134A. Okay. Carbon atoms 1, hydrogen atoms, fluorine atoms, and it's an unbalanced isomer. 700 series, third number from right indicates the series. Next two numbers are the molecular weight. Refrigerant cylinder color codes help prevent actual mixing. They're not a requirement for all manufacturers, so always read the label. Identify the refrigerant by the ASHRAE number. So again, we have the refrigerant and we have cylinder color codes. Okay, so R12 is a white cylinder. R22 is a light green, it's an HCFC. R410A is a rose colored. Okay, R404 would be an orange. So refrigerant color codes are pretty important, but always read the label as well. Toxicity and flammability is very important for refrigerants too. Class A refrigerants are not known to be toxic at or below 400 parts per million. Class B refrigerants are known to be toxic at or below 400 parts per million. Flammability ratings, all refrigerants are rated on a scale of 1 to 3. 1, no flammability. 2, low flammability. 2L, low flammability and slow burn. 3, high flammability. So every refrigerant is scaled A and B 1 through 3. Low toxicity, high toxicity, and flammability. So when we take a look at the refrigerant safety classifications, R22 is an A1, not known to be toxic, and low flammability. R410A, again, A1, not known to be toxic, low flammability. R600, which happens to be the propane. A3, low toxicity, extremely high flammability. It's good to know what these mean, because if you ever have to braze around these systems, or if you have an electric spark around these systems, you want to know how fast you need to get away from it and what precautions you need to take. The pressure-temperature curve shows a relationship between the refrigerant's temperature and pressure. It's used to determine if a unit is operating at the correct temperature or pressure. We have other methods to determine the temperature. We have pressure-temperature charts, and we have approximation using tubing or skin temperature. So every refrigerant has its own pressure-temperature curve. Okay, we have a fixed volume of refrigerant in a system, so the volume doesn't change. Let's drop back to our gas laws. Volume doesn't change. If we increase the temperature, the pressure is going to change. If we know the temperature and pressure, we can tell what type of refrigerant is in the system. If we know the pressure and the refrigerant, I can tell what the temperature is of the saturation point. Values are specific to one refrigerant. It's used to compare with measured values. values are for saturated refrigerant conditions. In other words, in the center part of the evaporator and the center part of the condenser. These are always available as cards, folded paper, and more importantly now, electronically. I can pull these up on my iPhone or Android devices. So if I know I have a pressure of R134A at, let's say, 30 psi, on the low side, my evaporator temperature is 35 degrees. If I have a pressure of 6.5 psig on my low side, I have a temperature on the evaporator of 0 degrees. Pressure enthalpy tables are lists actual operating temperatures and pressures. It shows the volume of 1 pound of vapor and the density of liquid refrigerant at a given temperature. It shows the enthalpy of that refrigerant, that's called heat content. Vapor heat content minus liquid heat content equals latent heat. This is a pressure enthalpy table. Okay, it tells us the given pressure, it's always in psi-A for these tables. Okay, it tells us what the vapor volume is at that temperature. It tells us what the liquid density is, because right there at saturation point I have vapor and liquid. And it tells me how much heat content per pound. That's BTUs per pound. Now this is important for designers. Okay, not so much for techs, but you do have to understand where these numbers are coming from and what goes into the design of a system. Okay, from a design standpoint, it's important because for a specific volume, I have to be able to move a certain amount of heat at a certain amount of pressure. We also have pressure enthalpy diagrams. I'm not going to go into them too much, but it's a visual graph of thermodynamic properties. It contains the same information in the pressure enthalpy table, but it's used to help understand how each component functions in a refrigeration cycle. It shows temperature glide for zeotropic blends. So again, this is a temperature enthalpy diagram. Shows us temperatures, shows us enthalpy, which is heat content, shows us the saturation curve. Okay, it shows us the saturation curve for each part of the blend. If I look at the tables for R134A, I will see this type of setup, okay? This, again, shows the same thing here. We have the temperature, we have the volume, with the enthalpy, and we have the quantity. And based on this, I could say at a specific temperature, okay, and pressure, what the heat content is. So points A, B, C, and D are my 4 major components of my refrigeration cycle. So the coefficient of performance is the ratio of refrigeration effect to heat of compression. Higher coefficient means better efficiency. It's used to determine which refrigerant will be most effective in a specific system. Coefficient of performance, refrigeration effect divided by the heat of compression. Refrigerant applications are designed based on pressure, temperature, and heat properties of a refrigerant. When the designers design a system, they think about the boiling point of a refrigerant, they think about the latent heat of the refrigerant, they look at operating temperatures, operating pressures, and equipment size, which would be the volume of the refrigerant it contains. We have some phase out of refrigerants we have to think about. CFCs, phase out completed in 1996. It can still be purchased from a stockpile by EPA certified technicians, but there is not much left. Okay, and it's very expensive. HCFCs, the phase out should be completed by 2020 in the US. It's illegal in new equipment since 2010. And there should be a complete phase out by 2030. Okay, now the 2020 phase out is the cease of production. Okay, there will still be some around for a long time. but the pricing on new refrigerant for R22 has skyrocketed in recent years. Commonly used new refrigerants, these are the ones that are going to be around. R134A is used in automotive and transport. R404A, medium and low temperature refrigeration. R407C, it's a retrofit for R22 equipment. R410A, new air conditioning. R508B, low temperature equipment. R1234YF, automotive air conditioning. Okay, now the primary ones you're going to be dealing with in residential and light commercial and commercial air conditioning is the 410A. We are not seeing a lot of use on the R407 for one very simple reason. It has a very bad fractionization rate. It has a very large temperature glide, and in older equipment that might have minor leaks, once you put it in there, you really don't know what you're going to end up with because of the blend. R717 is ammonia. It's a chemical compound of a combination of nitrogen and hydrogen. It has a very low boiling point. It can reach temperatures below zero without pressures below atmospheric. It's used in large refrigeration effect with small machinery. There's some hazards with it. It's flammable at 150,000 to 270,000 parts per million. So it has a high flammability, and it has a very strong effect on the respiratory system. You cannot inhale it. When working with ammonia, you have to wear a tight-fitting respirator. Again, you cannot inhale this. You always stand off to one side when operating an ammonia valve. You use a sulfur candle or spray vapor to detect leaks. You want to follow all training and safety protocols. You're going to be specially trained if you handle ammonia. Another refrigerant in use is cryogenic fluids. It's used in processing plants to rapidly freeze food. They rapidly freeze reduces ice crystals, and it results in less damage to food during freezing. It must be kept in insulated vacuum containers. It is expendable, meaning it does not get recovered. When handling cryogenic fluids, never allow the fluid to touch your skin. This is stuff like liquid nitrogen, liquid oxygen, liquid carbon dioxide. Okay, be careful on this stuff. You want to protect your entire body with suitable clothing, helmets, and gloves. Expendable refrigeration system releases an expendable refrigerant to the atmosphere after its use. Refrigerant is not collected or reused, and it's also called an open cycle or chemical refrigeration system. For example, liquid nitrogen into a conditioned space. Now, be very careful with these systems. If you have to enter a space where this is used, make sure you wear a respirator or the space is completely vented. Most of these refrigerants you cannot breathe. Refrigeration lubricants are charged into a refrigeration system. It lubricates contact between moving parts, and it must be able to travel freely through all parts of the system. The characteristics of refrigeration lubricants: low wax content, high thermal and chemical stability, low pour point, low viscosity. Wax content is important. Wax separation precipitates out of lubricant at low temperatures. It can plug control orifices and clog systems. Flock test, FLOC test, determines how easily wax separates. The flock point is the highest temperature at which precipitate occurs. You have thermal stability and flash point. Thermal stability is the ability to remain stable in high heat areas. Chemical stability, ability not to react chemically with refrigerants or other substances. Flash point, the temperature at which vapors from lubricant surfaces ignite. All of these, as you can see, are important in a refrigeration system. Viscosity is a measure of a liquid's resistance to flow. It changes with temperature. High temperature reduces viscosity. Low temperature increases viscosity. Pour point is the lowest temperature at which a lubricant will flow. Since the lubricant goes through the entire refrigeration system and must still flow at cold and hot temperatures, this is important. There's some different types of lubricants. The type of lubricant has to match the type of refrigerant. Mineral oil is used in CFCs and HCFCs. Polyester oil is used in CFCs, HCFCs, and HFCs. Alkylbenzene oils are used in CFCs, HCFCs, and blends containing the others. Polyalkylene glycol is only used in HCFCs. Again, make absolutely sure you're using the correct oil for the compressor and the refrigerant. You cannot mix oils. So there's a chart that's available for most refrigerant that tells you what oils are appropriate for the different systems. Okay. And this is a lot of times why you cannot convert one system to another. So for example, if you have an R22 system, okay, R22 uses alkylbenzene or mineral oil, and you want to convert that to R407A because 407 is a drop-in. You have to be able to actually empty all the oil out, convert the system over to polyester oil. You cannot just put in R22 oil. When you handle refrigerant lubricants, you need to keep them in sealed containers. Most will absorb moisture. You need to transfer lubricants in chemically clean containers and lines. You don't want to expose them to air or moisture. You want to buy small sealed containers. Reseal the container after withdrawing the lubricant. Unused lubricant may pick up moisture or dirt, and you do not want moisture in a refrigeration system. To adding lubricant to a system, make sure you have the correct amount of lubricant. Too little shortens components' life, specifically the compressors. Too much reduces refrigerant pumping capacity. Follow the manufacturer's recommendation. Make sure the lubricant is compatible with the refrigerant. Do not mix lubricants, and add lubricants only if there's signs of leakage. Lubricant should be translucent. Evidence of its impurities in lubricants is discoloration, odor, metal shavings and chips. You want to make sure you replace contaminated lubricant, and you want to replace system dryers and filters.